Welcome to Physics Exam Prep. In this lesson, we're dealing with a graph problem. In earlier videos, we've already seen graphs like force versus time, where the area under the curve represents impulse. Here, the axis labels are different. So if you don't read them carefully, you will lose marks. Why don't you pause the video and give it a try first? Alright, how was it? If you got 500 joules for the answer, you're already ahead of many classmates. You know, I don't pick easy ones for these videos. Let's interpret the question and decode what the examiner is really testing. Here's a setup of the question. An object starts at rest, gains energy from a push force, and it begins moving. Along the way, it loses energy due to friction. The question asks about its kinetic energy. This is a classic energy change problem. So the first step is to organize the information into energy gain and energy loss. The energy gain comes from the horizontal push force doing work on the object. From your school notes, work done equals to force acting on the object times S, the displacement of the object traveled. This is true only when force is constant. More generally, work done is the integral of force over displacement. Don't panic. You're not tested on integration in IB physics. Just remember, work done is the same as the area under a force displacement graph. That's it for energy gain, and let's move on to energy loss. Energy loss comes from friction. Here, the object is doing work against the frictional force. In other words, that part of the energy goes into fighting friction. That's why the energy decreases. Since friction is constant mentioned in the question, we can now use W equals to F times S to calculate energy loss due to friction. Let's illustrate the relationship between initial energy, energy gain, energy loss, and final energy. The object starts at rest, so the initial energy is 0. Then, as the push force does work on it, the object gains energy, shown here as moving up to a higher energy level. Next, the object does work against friction. That's why the line steps back down. Energy is lost to friction. Finally, the question is asking for the kinetic energy at the end. That's just the difference between 0 and its final energy level. If you study chemistry, you'll notice this looks just like an energy level diagram from energetics. I'm using this because it makes the idea much more straightforward. And keep in mind, examiners can flip the setup. They might give you the final energy and energy loss, and ask you to find the energy gain. With this diagram, the path is always clear. Here's something extra for you to think about. What if the initial velocity wasn't 0? How would you work out the final energy then? Drop your ideas in the comments. I'd love to see how you would tackle it. Let's walk through the solution step by step. First, calculate the energy gain, which equals to the area under the graph. And we get 600. Next, calculate the energy loss due to friction. We can apply the equation force times displacement here because the frictional force is constant. Plug in the numbers and we get 100 joules. The final kinetic energy would be energy gain minus energy loss. And we get 500 for the final answer. Let's have a recap. In this lesson, we learned that for energy problems, always organize information into energy gain and energy loss. And for a force versus displacement graph, the area under the graph represents work done. Now, an important note. Students often get confused between work and energy. Do you remember in the last video when we talked about impulse and momentum? Impulse is a cause, and the change in momentum is the effect. The same idea works here. Work done is a cause, and the change in energy is the effect. Work done is a cause because it's the transfer of energy that happens when a force acts through a displacement. And a changing energy is effect because it's the outcome of that transfer, showing how the object's energy increases or decreases as a result. Here's a simple analogy. Think about stretching a spring. The work you do while pulling is a cause, and the extra elastic potential energy stored in the spring is the effect. That's all for this lesson. If you've got a different method, I would love to hear it. If there's a topic or problem style you want more of, suggest it in the comments. See you in the next lesson.